have you done so far? Have you worked on the homework? Have you watched the lecture video? Looked at the next
Yeah, I have done the homework and the discussion.
one? Okay. So what did you think of section 4.6 stuff?
Um, I think it's easier than the last one.
Oh yeah. Oh God. 4. Oh, what was last? 4.4
Yeah.
is a lot about just sort of intuiting what you need to
Mhm.
do. Just look at it and figure it out, obviously.
Mhm.
Whereas this is a completely algorithmic approach. You
Mhm.
do these steps, you get the answer. It's a unique answer, so it will be right. Like that is all. So it's a lot more comforting in that way. It also um, relies a lot. Well, its underpinnings, at least, rely a lot on linear algebra. So I wasn't sure. What is your background with linear algebra?
Um, I don't know. I think I so in high school in Brazil we take matrices, this kind of stuff,
Okay.
but
Yeah.
that's all.
Okay.
I
So similar when I was coming into undergrad, I had seen matrices. I had added matrices before, and I knew that multiplying matrices was complicated. I think I had done it on a couple small cases before. But that was all. I didn't know anything about like, oh geez, Gauss-Jordan elimination and things like that. Like the sorts of things that literally any basic linear algebra course should teach about.
Mhm.
I had just sort of vaguely been introduced via calculus. So this is a lot more like the being vaguely introduced via calculus. But I wanted to point out some of the things that are going on here behind the scenes, why this is working. And it's really interesting. So this, of course, I mentioned this is the first section where we have any kind of algorithm for finding particular solutions, which is really awesome. It doesn't require any obscure intuition, but it does require quite a few Wronskians. So, as a brief review for those of you who will need it, um, just that this is the form of the Wronskian, right? We're talking about a set of functions. These are usually, we're talking about the solutions to the homogeneous differential equation. And we line those up in the first row of a matrix. And then for each subsequent row, we take further derivatives of those, not necessarily n
Mhm.
many functions. They'll wind up taking n minus one derivatives. Um, but from there, this becomes really simple, right? This is just Laplace expansion of the derivative of this matrix, and that is the definition of the Wronskian. Okay, we saw this in 4.1. 4.1 also gave us a theorem that said that the Wronskian is non-zero if and only if, well, assuming these are solutions and many solutions to an nth order homogeneous linear equation on an interval, okay, all of that needs to be met first, but then this Wronskian is non-zero if and only if these are linearly independent, um, which is to say that this becomes a fundamental solution set on that. That's important because of the linear algebra underpinnings here. For the simplicity of notation, I'm going to treat everything as n equals 3, which I'm sure is why I said that out loud. But this all generalizes really nicely.
Okay.
So variation of parameters will uniquely find a particular solution of this form given that we have a general solution to the homogeneous differential. By variation of parameters, we're specifically saying we are varying the parameters of these equations. We're taking this homogeneous equation and taking those constants that are fluid. We could plug anything in there and get a solution. And we're instead plugging in these functions in terms of x to see, um, well, I was going to say to see if there is a particular solution. Well, it turns out there is, as long as this is a linearly independent set solution. There
Mhm.
will be a single unique particular solution that can be found via this method. So a detailed explanation is complicated, but is given in your book in the first few pages of this section. You can go through the specifics, looking at, they relate it back to the solution of linear differential equations of small order that we had looked at, first order equations. If we start looking at linear second order differential equations, this intuition that maybe there should be a particular solution of this form turned into, okay, well, if we plug that in, how does that actually expand? How does that turn out in the equation, differentially? And by expanding that and canceling things, we're including assumptions here that are necessary for the linear algebra to go through. This all simplifies very nicely to a system of equations that could be written like this. In your textbook, it is not written like this, but this gave me a little bit better understanding of what was going on. All we're really doing here is taking this system, y1 times 1 prime plus y2 times u2 prime plus y3 prime equals 0, etc., multiplying these matrices together. And that's all written explicitly in your book if you want to see the way they have it written. We're just solving this system of equations where the unknowns are these u's of i's. y1, y2, y3 are either given to us or we can solve for them with our skills with homogeneous solutions. And g of x is just the right side. I don't have, dang, I usually print the generic form of equation at the top. But g of x is just the right side of that differential equation. If this were homogeneous, it would just be 0 on this side. Hence, in linear algebra, you would call that homogeneous system of equations. So that all makes sense. All the things tie together. But yes, g of x is just the right side of that equation. So I spent a long time for myself digging why each of these pieces was chosen as it is. Why are we having y primes here? Why not u? Why not just u? And that has to do with the expansion when you plug this in as what you wind up with is some complicated thing where you wind up with the first two rows of this system of equations plus the last row of the system of equations. And so by assuming that these equal 0, we can focus on this one, right, equaling g. So it's a little bit complicated in summary. Okay, but the reason at least one of these questions that I can definitely answer quickly is why all zeros? Why are we just assuming randomly that this equals 0? Why are we allowed to do that? Why are we choosing to do that? Do you know?
I don't know.
My intuition before digging into it was that anything would work, but we chose, and that happens basically a lot in linear algebra. You can always choose a different basis than the normal, nice living one, but good God, why would you do that? Technically, you could make all sorts of different awful bases. And in the same way, we could make a lot of different assumptions here and still have a unique solution. You could say that this was 2, 5 g of x or whatever. But that just winds up being really, really awful to calculate. And all we need here is a particular solution. All we need is there exists some answer. And so making this more difficult for ourselves is completely pointless. It's an example of choose the shortest path because you can. So these zeros are here just to make your life easier, so that we can treat this sort of as simply as possible. It would have the same, not literally the same solution, but it would have similarly a unique solution, as long as y1, y2, and y3 are linearly independent functions. Regardless of what you put here, it would have a unique solution. So we choose 0 to make our
Okay.
g of x is important, just by how this all expands. But yes, these two solutions are specifically so that we can make this system of equations. We have n equations with n unknowns, so we know that we'll have this unique solution as long as. Okay, so this system has a unique solution if and only if the leftmost matrix is invertible, which is to say, as long as the Wronskian of these three functions, these n functions, is non-zero, based on this theorem. These columns will be linearly independent as long as the determinant is non-zero. That determinant is the Wronskian. And if the determinant is non-zero, then the inverse of this matrix exists, and hypothetically, imagine this A times U B situation, and you could turn this into U equals A inverse times B. And so just by matrix equation, this makes sense. It will have a solution. You can just turn this around, calculate whatever comes out on the right. That is your answer, regardless of how it moves. But we actually would really rather not calculate the inverse of this matrix because that can get really, really, really ugly. So instead of doing that, we make use of Cramer's rule, which is I think in this case, it's by far simpler than trying to compute the inverse. Although, if you've heard of it at all, those of you watching, or in particular, Julia, if you've heard of Cramer's rule at all, you probably heard it in a context where it wasn't. In a context where these are numbers, anyway, instead of functions. And in that case, it's not necessarily faster than just. Anyway, in this case, it's very nice. So Cramer's rule applied to the system above says that as long as the Wronskian is non-zero, because you're which is the same idea as long as the determinant of this is non-zero, we can find an inverse. As long as that Wronskian is non-zero, and we label this W1, W2, W3 by replacing the ith row with that right-hand column, 0, 0, gx. And it's all zeros all down to the n component, whatever n is, with g of x as the last term. By replacing the ith column with this column and calculating the determinant there, we can solve this by saying, okay, the first component of this vector is going to be this determinant divided by the original. So this is all heavy linear algebra, essentially. But it becomes beautiful in practice. It becomes a beautiful algorithm. So, and this is for any I, for all I. Using this, we can solve for ui prime. And then by integrating, we can solve for the original. So from start to finish, we're finding homogeneous solution then considering, well, what if we replace those c's with functions of x instead? We set up this system of equations, so you don't have to this way. Really, you just have to care about the Wronskian. We're checking, is this Wronskian non-zero? And that's all we really with this sort of visualization. Is the Wronskian non-zero? Then calculate each of these for all n. Get out this, and by integrating, you get out the original. So then your particular solution will look. And then, of course, your general solution is just the sum of these things. And sometimes these u's will turn out to be constant, right? So if you're writing the condensed version, or if you're checking your answers against something, some of these might get collapsed into the original homogeneous solution. Some of them will just get absorbed if these are constant. But as long as these u's are non-constant, they will tack along on the end for the general. Okay, so all of that, let's work an example. Okay. Example, find the general solution of the following variation of parameters. Okay, so we have y double prime minus 4y prime plus 4y equals x plus 1 times e to the 2x. Okay. Where do we begin?
The auxiliary equation.
Exactly. So I save a ton of space in my own work. I write it just immediately beneath it. Of course, as always, remember that y itself is to the 0th derivative. So this is m raised to the 0. Okay, so, and we're talking about homogeneous equation here when we're finding this auxiliary. So this is m minus 2m minus. So that we have comma 2. So our homogeneous solution of y1 equal to e to the x, y2 equal to x, x. So that our homogeneous equation solution is going to be like 1 x plus x. Okay.
Yep.
Once in a while, I'll make just a. Okay, cool. So we have this, we have these. These are what we want to focus on now. So what we want to check is that the Wronskian is non-zero. And that's something we should check with anyway. I guess technically it should come even before this. Right? Technically, this is only true if these are linearly independent. Of course, we know that the Wronskian will be non-zero because they're identical but with an x, right? So we know that these will be linearly independent already. So, but for this method, for variation of parameters, we will need to actually calculate. So w will be equal to e to the 2x, and then their derivative. So we have 2x, and this is going to be much space. E to the 2x plus 2x. Okay. So the Wronskian of this, just the determinant of this matrix. On the main diagonal, we have e, I'm just going to distribute as 4x plus x 4x minus 2x So this is just equal to e to the 4x. Of course, this is never 0, just because of what we know about e.
Mhm.
So this. Now we want to calculate our w sub I, right?
Yeah.
So when we're thinking about this system of equations, we're filling in this right-hand column for the ith column when we're calculating this w sub i's. So the column that we're going to be substituting in here is going to be 0, 0, what? It's only two functions. So 0, and then x plus 1 times 2x. I'm pointing at it, and it's off the screen. Here we go. So that's going to be the second component of this. So W1 will be equal to the derivative of, or the determinant of, 0 over
Yeah.
beside the normal second column of this room x under x. Okay, this, well, the main diagonal is equal to 0, and that will always happen, by the way. There will always be, especially in 2 by 2, but even given the 3 by 3, there will be ways to make this shorter, because in a 2 by 2, if you're replacing this where all but one of the entries, or one of the entries is 0, then one of these diagonals will always be 0. Got it. So, okay, convenient. Then you're subtracting the off diagonal, so this will be negative x 1 times e to the 4x. I don't think that simplify in any way that's helpful, so I'm just going to stop there. I found out while I was working these problems, both the lecture and through the textbook, that I have a tendency to simplify things and then later regret having simplified them, especially when it comes to trig identities and things like that. I'm looking at all sorts of problems in this section where we have sine over cosine, and I'm like, oh, that's tangent, or like, oh, that's just going to be 1 over sine. And I write it that way instead, and then 2 lines later, I'm just like, oh, right, I'm integrating now, and I would rather think of this as sine over cosine. Okay, that's fine. My whole experience, I was sharing that with a friend while I was doing my entire experience in mathematics has been that my intuition tells me to do way more work than I ever do. Alas. All right, so w sub 2, e to the 2x, 2, 2x, and then this column, 0, 1. Main diagonal, of course, the off diagonal will be 0, but the main diagonal is just x 1 times e to the 4. Okay, so we have our w sub i's. These will each imply our u sub I prime. So this, that u1 prime is equal to w1 divided by w.
Yeah.
So the e to the 4x cancels, and we're left with just negative x times, or a negative x squared. Since we know we're going to be integrating this, it's just this way. And this one implies that u sub 2 prime is equal to just x plus 1. Again, these. Nice. Those are beautiful, beautiful answers. Because we know that we're integrating and these are just polynomials. It's very nice. So then this tells us that 1 is equal to the integral of negative x squared minus x. This is equal to negative 1/2, no, third, actually a third. Okay, negative 1/3 x a third minus, here we go, 1/2. And we don't ever have to put the plus c on this. The reason is, like I was saying, if any of these u's come out to be constant, then they just get sucked into that homogeneous solution, right? Or here, where here. If you were writing out your general solution, you have this c times each of these plus whatever u is times each of these. And if u itself turns out to be constant, or if part of u is constant, that's just being added on, had a plus c here, then we would have just a plus, another plus c6 times y3, right? And it would just get sucked into this. So we never have to worry about it, which is nice. It's convenient. And 2 is equal to the integral of 1 x, which is equal to 1/2 squared plus. Okay, so we've solved for our u's. Now what?
Now you have to multiply it by y.
Mm-hmm. Exactly. So getting our particular solution, we know that y sub b will be equal to 1 times this. Let's see, our y1 was 2x. So we have, and I don't personally believe in simplifying this work any, or expanding this. It's going to be ugly regardless of how you write it. Actually, it's going to be correct, but not pretty to look at, which is fine. Okay, so at the end, the only real thing to make sure that you're keeping an eye on is that you're not mixing up any of your eyes. Remember what order you put these original y sub i's in, because it will change your answer drastically. In fact, it even matters like which order you put these columns in the middle area. You can wind up with wrong answers. Interesting. I think it's should only differ by minute. Okay. 1/2 squared times y2 x. Okay, so our particular solution is this. None of this is actually getting absorbed into the homogeneous solution in this case. So our homogeneous solution our general solution will be y equals this homogeneous solution, b1 equals x plus x, x plus, and I'm just going to say, sake of this all. Do you feel comfortable enough with this process? Okay, cool.
I'm not sure about the second example.
What's that?
The second example, I think I miss multiplication maybe.
So what I messed up in this second example when I worked it first was that I didn't put this into standard form. And that results in having no, essentially being off by a factor of 4. Because
exactly. That's the thing.
Exactly. Yep. I did that the first time I solved this. I got to solving all, my Wronskian and plugging in my W sub i's. And when you calculate the W sub i's, you get out wrong value. The reason is because they have given you a non-monic differential equation. They've given you something where the leading coefficient is not 1. And so be careful.
So it always has to be a 1 in front of the
Yeah,
first.
it will.
Uh,
I had forgotten. But
Okay.
yes, for this method to work, you have to be dealing with a monic differential equation to start. So
Okay.
the first step in this will be to divide by 4 in all of
Okay.
this.
Hmm. Right.
Okay. 4y double prime plus 6y cosecant. So the first step, this is equivalent to saying y double prime plus 9y 1/4 cosecant. And this is the necessary form even before you start talking about your homogeneous equation and your auxiliary equation and all of that, so that you're not off by a multiple. So then this squared plus 9 is plus or minus, that was a weird, minus 3i times m plus, so that m is equal to plus or minus 3. There, better. Of course, this will give us the okay, good. So what we saw in was it 4.1 or 4? Or for how to solve this sort of thing, we'll have linear solution that's e to the alpha x times cosine of beta x plus e alpha x sine beta x. Of course, our alpha here is 0 and beta is 3. So we just have cosine of y2 sine. Okay, and from here, it should be the whole same process. Okay? So we have our Wronskian x sine negative 3 to 3 cosine squared x plus negative 5. This is equal to 3 times static. Just. Of course, it's good to note that this is, I'm going to say not equal to 1. Also true, but not useful. That this is not equal to 0, just because that means the rest of our process is legal. If we were to get 0 at this point, I'm not sure that we have any method to approach this. So certainly not any algorithmic method to continue on this problem if this is equal to 0. Technically, if you can prove some other way that these are linearly independent, then you could continue. But what we really need is for this. Could we? Because then this determinant is 0. I think that we wouldn't be. Yeah, because it's if and only if, of course. In the case of these being solutions to an nth order differential equation, this is an if and only. So if this were 0, then we know that the determinant of this is 0. This cannot generate a. Okay, at least by this. Okay, moving on. W1 will equal, replace the first column with 0, 1/4 cosine of x. So, and the second column stays the same. So that this determinant is negative 1/4 period. Negative 1/4 of sine 3x times secant x. But this, of course, is just sine over sine. This is equal to negative 1. W2 is equal to, first column same, second column is this section is a lot of computation. The most important parts are understanding why each piece of this is able to work. And beyond that, it's a lot of just, okay, now do it again. Okay, now do it again. Okay, now do it again.
Mhm.
Okay, so this is to cosine. This is an example of the cosine over sine that I'm like, oh, that's cotangent, and I'll write it as cotangent. 2 steps later, like, oh, right, I actually just want this 1/4 secant is equal denominator. Okay, so when we're solving for u's, then u prime is equal u sub I prime is equal to w sub I divided by w. So we'll have u sub 1 prime is equal to negative 1 over 12, negative 1/4 divided by 1 integral of, well, actually, you could say, well, never mind. Say something that's false. If u turns out to be constant, then you don't have to worry about it further because it'll be absorbed in. If u prime is constant, that is not the case. So, okay, this which is equal to just negative 1/12. 2 prime divided 12 by 2 is integral of that. Of course, we want to do a substitution here where u is equal to sine, so that we have 1 over u times du, or geez, how about we v equal to sine of x so then we can do this substitution, that this becomes something. And of course, this is just 1/36 times the natural log of u, or dang it, I decided to use v instead, and my hand immediately betrayed me. V's, okay, we're substituting with v's. But the natural log of v, which in this case is cosine, and almost always, sorry, this is really scrunched in the corner, but almost always in this class, especially, people will disregard these absolute values symbols because they're completely unnecessary. Just intuitive, like you know that you can't plug something negative in there. So yes, you're just going to X that give you positive things. I always keep them just for okay, so we have U1, we have U2. The only thing left in this, we're solving general solution. Solve. Well, anyway, the general solution of this then will be your C1 times Y1, C2, Y2, and then U1 times Y1, U2, 1, cosine C2, sine, minus 112 x sine plus 36 sine of 3x times sine, period. Done. All good?
Mm-hmm.
The first two examples that I have, they're just sort of an opportunity for you all to practice stuff so that you can really see how this is working. But the third example that I have is specifically looking at a third order. Not only because it's more intimidating to look at, but also just for practice with really working with a higher dimension object. So, okay. This is solve the third order differential equation using a parameter. We have y triple prime. Oop, off the screen. Here we go. Y triple prime minus 2y double prime minus y prime plus 2. First step, double check this is monic. Okay. Then move it into auxiliary equation. Cubed minus 2m squared minus m plus 2. If your algebra skills are on point, you should immediately notice that this is factorable by grouping.
Mm-hmm.
This will be looks similar enough that we've got this m times m squared minus 1 minus 2 times m squared, hence 2 times m squared minus 1, which is equal to m minus 2. And this is a different squares plus 1. Okay, so we have m's equal to, I'm going order 1, 2, and negative 1. So that we have our order for y1, x, y2, 2x, and 3 is for our linearly independent. Well, technically we don't know that they're linearly independent, but our solutions to the homogeneous. So for degree 3, we will have a 3 by 3 Wronski. We'll have to compute the second derivative of these, but they won't be difficult because they're all e. So w is equal to x, e to the x, e to the x. Okay, great. E to the 2x, 2 e to the 2x, or e to the x. negative x, negative, negative x, negative. So this shouldn't be too bad. I chose to expand based on the first column, the Laplace expansion.
Mhm.
You can totally do whatever you want, but I think that's the easiest in this case. So this is equal to e to the x times derivative of the bottom row. So x times 2 times e to the 2x, e to the negative x. Well, the exponents will come together, so they'll be x minus negative 4x. So then next we'll have x with expansion. So exactly what to tell you for if you have any trouble remembering this stuff. Except that, gosh, I had so much trouble as an undergrad remembering where the heck this sign needed to change. But it's just steps from the order. Minus e to the x times e to the 2x times negative x minus 4x plus last x this corner times negative minus. Okay, so this is all equal to e to the x times 6 e to the x in this minus e minus, good, great. So these cancel, and you're left with just 6e to the. Okay, this again is non-zero. Awesome. You technically should always check that. So then continuing, W1 will replace the first column of this Wronskian 0, 0, e to the 4x, because that was our right-hand side. So 0, 0, 4x. And then the two more complicated columns, x, 2e. Negative x, negative, negative x. This is equal to, I'm obviously going to expand on the left column because anytime you have that many zeros in a row, you definitely. So we'll have just e to the 4x, double check whether it's positive, negative, it's 2 steps down, so it'll be positive. 4x times top corner will just be negative to the x minus 2 negative 5x. Yeah, that's W2 will equal, so all of these Wronskians should be just one step like that. It should be just the size of a determinant of one size smaller, because you will always have one column that's all zeros except one spot. So it'll just be that entry times the corresponding other. Yeah, e to the x, e to the x. 0, 0. Negative x, e to the. I'll expand on this row, so I have e to the 3, we'll have negative e 4x times remaining column. So you have negative 1 minus 1. Double good. This is equal to negative 2 times negative things. 2. If at any point I am skipping too many steps because
It's fine.
Okay.
I
I don't
have
want
a
to just
problem.
go drudgerously slow, but
yeah, I only have a question in the end of this.
okay, awesome. Okay, so this is 4 steps positive for x times the remaining 2 minus 2. Yeah, okay, it is. I keep psyching myself out on this one because I know what the answer is supposed to look like, and I keep being like, no way, 7's way too big.
No, it works.
It does. Okay, so then we have that this implies 1 prime is equal to this divided by this. This is our W context. So divided by 6e to the 2x, these will cancel so that we have negative 1/2 3x.
Just saw what I did.
Aha! Perfect. Which
Yeah.
part did you mix up?
When I was no, I think it's fine. No, it's just when I was doing the division. No, it's fine. I don't know what I did yet. Okay, continue.
Yes.
Okay.
2 prime will be equal to 1/3 x 3 prime 6 5. Okay. Oh, not much of a point. Okay. So u1 will be the integral of negative 1/2 3x. This will be equal to, well, the e to the 3x would have had a 3 spit out. So this should be negative 6. u2.
Oh, I thought I wasn't integrating. It was.
Aha!
Yeah.
Yep.
Great. Okay.
Integral of 1/3 2x. Of course, this one would have spit out a 2, so it will also be 1/6 the 2x. Yes. 3 will be the integral of 6e to 5x. Of course, this would have spit out 5. I had
1 above 6, 1 and yeah.
Supposed to be 1/6.
Yeah,
Yes. Here we go. Give me parentheses there. Parentheses here. Okay, yes, 1/6. That makes much better sense.
Yeah.
So this would have spit out a 5, so we have to be sure to divide by that as well. Get 1/30th e to the 5x. There we go. So then, using this, our y-subscript p is equal to u sub I times y sub I. So back all the way up here. Y sub p is equal to negative 1/6 e to the 3x times x will be 4x plus 1/6 e to the 2x plus 2x will be 4x plus 30 5x plus 5. Well, and so we see that these two cancel out, and we're left with just this for our particular solution. So then our general solution here will have just e1 e to x plus 2 e to 2x plus 3 e to the negative x plus this particular solution 30th.
Okay.
So the 3x3, it is more work in the way of Wronskians, but it's not harder. It's still exactly as algorithmic. You will always have a determinant of size at most -1, right? And so, and I don't think that you will ever work a problem, at least in this class, of this sort that is higher degree than. Technically, one of the discussion problems gave an example that was 4th degree, but it gave you 2 of the roots just outright. And so then it just becomes a factoring problem. So I think that this is about the most difficult type of problem as far as size. Okay, the very last problem that I have, and it's 3 o'clock now, so I will wrap this up really quickly, is an example in your book. Well, but I just wanted to. Its solution doesn't come out looking nice at all. And there will be cases where you'll get these u primes and they will not be elementary functions. So in the case that u prime turns out to not be elementary, which is to say that it doesn't have just sines or cosines or some nice way that we know how to integrate, case wind up with e to the t divided by t and 1 divided by t e to the t as pieces of it that we have no tools to deal with in any nice way. And so we just leave them as integral defined functions, the same way that we did at the start of the semester when we were talking about equations that didn't have very nice looking answers. Okay? So just going to. So this is monic. We can put this into m squared minus 1 m is equal to plus 1 y1 x y2 negative x. Nice. Approach our Wronskian. Know that x negative x negative this Wronskian to negative 1 1 negative 2 is non-zero. Hooray! Okay, so w1 is equal to 0 negative e to the negative x. This is equal to negative 1 over e.
Is that correct?
I think.
Just more. Okay. Okay. So if I do my ROM scan in another order, so I got a 2, not a minus.
Aha, yes.
That's a problem or no?
That's not a problem as long as you're consistent.
Okay.
Yep, so follow your own work then and make sure that your W1 is replacing that
Yeah.
proper. Yeah,
Okay.
exactly. So that's the only thing. I think that the only difference is sign in
Okay.
anything.
Okay. Yeah.
So we should have opposite signs up
Mhm.
until, oh God, possibly the end.
Okay.
At the very least, I know that this process spits out a unique answer given that you have these in the same order. I'm not sure it gives the same answer otherwise.
I think it does
The only difference is sign error that should.
because uh, mm,
So this u1 prime will be this divided by, oh, there it is. That's where it rectifies itself because you're dividing them. The
yeah.
only difference by swapping these columns is a change in sign. And so if you change the sign of W sub I and you change the sign of W, then it rectifies itself.
Mhm.
Yeah, okay, so we're back on track.
Okay.
This will be positive 1 over e. 2 prime will be negative x divided. The problem here is that these are both non-elementary equations.
Yeah.
And so we can't just just like hop into our integral and have a nice day. And so the way that the
I think
yeah,
you're missing the 2,
oh
right?
dang it, you're correct. This is
Okay.
divided by that 2 should be in the denominator. Yes.
Okay.
Yep. So worried about sign. But yes. So the way that we handle this, and I feel like we covered this nicely earlier in. So I'm not going to go into, but we wind up writing this as u1 is equal to integral from x naught to x of this thing written in terms of t. That the 2t times under 1 as our integral to, sorry, this camera keeps refocusing camera here. But yes, writing this as an integral defined function instead.
Mhm.
And u2 equal to not the negative t divided, so that our final answer will just be these multiplied by our y. General solution, y is equal to c1 times x plus 2 e to the negative x plus this ugliness, x naught to x 2e 1 times e to x plus this ugliness, not x negative, and you can technically pull constants out of here, but they would just be multiplied right in front. Your textbook does that. I'm not interested in more work for no profit. Okay, times e to the negative. Done. Agree with your solution?
Okay. Okay, that's fine.
Cool. textbook writes it a little bit differently in their solution, but it's all equivalent. All right. Do you have any other questions?
No.
Okay. We have a problem set next week. Woo!
Yeah. Excited.
I'm so excited. Means I don't have to try and search for a good discussion. Get a break. Ooh. Plus somebody else is grading, so I don't even have to grade it.
That's good.
Okay. As long as you don't have any other questions, I will stop recording here.
Okay. Thank you.
Yeah, thank you so much.
Have a good weekend.
Yeah, you too.